I'm Andreas. I'm going to be talking today about keys and wallets. If you have questions, jump in and ask the questions at any point in time. I'm going to be leaving in about an hour, and then those of you who have more knowledge are going to be answering questions for those of you who have more questions. Right? Because this is a community after all, and I'm just up here to serve a role. Today we're going to be talking about keys and wallets. This is just a checklist of what I want to cover. Elliptic curve cryptography, generating keys, formats of keys, type 1 keys, type 2 keys, bit 39, bit 38, Shamir secret sharing system, and paper wallets. We'll get to as much of that as we can. So how many of you are here for the first time in this meetup? Welcome! All right. So the meetup works like this. We go, Mondays we do seminars, and Sundays we do hackathons. On the Mondays we have someone who can talk about a technical topic, present some information, and do Q&A. You then go away and do your own study, research, coding on that. And then the Sundays we get together and we do a hackathon, where we collaboratively code and exchange ideas and work on projects. And the idea is to figure out if the information that the person in front provided on Monday was actually correct. Now, the correct answer is no, it wasn't. It was only partially correct. And during the hackathon, we found out exactly what bits the person got wrong. That'll be me today, okay? So I will get some things wrong. And I'm going to do some of this from memory. The rest I'm going to be looking at my notes here. This is all information that's available in various bits and pieces all over the Bitcoin wiki. And I'm going to cover it at a number of different levels. If you have questions, jump in during the presentation and ask me those questions. All right, so how many of you are familiar with Bitcoin technology at the moment? Okay, that's good. How many of you understand public key cryptography at a basic level? Okay, who does not understand public key cryptography? It's perfectly fine if you don't understand public key. Okay. Yes. How many of you understand elliptic curve cryptography?
Understanding
a verb. Can draw the pretty pictures, not can run the equations.
Can draw some pretty.
Okay, excellent. Which is about as much understanding as I have. All right. So let's start by some basic terms. A Bitcoin wallet is not a wallet. It's a keychain. Bitcoin wallets have no coins. The coins are on the blockchain, on the network. The wallet has keys in it, which is why calling it a wallet was a monumentally stupid decision that will come to haunt us, because it's not a wallet, because it doesn't have coins in it. It only has keys. So it's a keychain in every sense of the word, both metaphorically it's a keychain, and in terms of public key cryptography, it's a public key keychain. Right? That's what a wallet is. Wallets are implemented in a number of different ways. The implementation of a wallet is application specific. Bitcoin D implements a binary file wallet in a very specific way. Multi-bit, different way. Electrum wallet, different way. Armory wallet, different way. Blockchain info wallet, different way. Okay? They all have the same basic information. Key pairs. Pairs of public and private keys. As well as metadata. Corresponding addresses and things like human readable names, labels. All right? What we're going to talk about today is not the wallet formats. We're going to talk about the keys that are in them and how they work. Yes?
Just to be clear, then wallets have nothing to do with Bitcoin.
Okay, so wallets have nothing to do with Bitcoin. In fact, none of the keys are stored on the Bitcoin network or on the blockchain. They are presented on the blockchain in order to create encumbrances. That means that on the blockchain what you will see is an amount of coins locked to a specific public key. And that is the only appearance that will happen on the blockchain. And then you will see those same coins unlocked when they're used as inputs and transactions by signature. that exposes the public key. So you will see both the public address and the public key of a key pair on the blockchain if it has been involved in a transaction. A really important thing to realize is you don't need to be online to generate keys. You don't need to be online to use those keys. You don't need to be online to sign something with those keys. All of those things can happen offline. The mathematical functions that do not depend on any information that's in the blockchain. We'll go into more detail on that. That answer your question? All right. So a wallet has no coins. It's actually a keychain. The coins are in the network. The keys are in your hard drive, and they are not in the network, although they sometimes appear in the network in order to signify ownership of an amount by locking, and to signify proof of ownership when spending in a transaction. That's the only time keys actually appear in the blockchain. So within a wallet, you have two types of keys. Private keys and public keys. These form a key pair. A private key is a number. It's just a number. It's a 256-bit number. All right. What is the best method of generating a random private key? Anyone?
Find a good source of entropy.
Find a good source of entropy. Excellent. Or dice, pencil, and paper. What I want to explain by saying that is you need no computers, you need no access to the internet, you need no blockchain, you need nothing other than dice or coin, pencil, and paper. How do I generate a private key with a coin, pencil, and paper? I flip a coin 256 times. If it's heads, I write 1. If it's tails, I write 0. At the end of that, I have a 256-bit random number, evenly distributed across the entire search space of random numbers. That number is a private key. Right? That's all you need. Programmatically, how do you do this? Programmatically, the most common form of doing this is to find a source of entropy. What does that mean? A source of entropy is a random number generator that has been properly seeded. And it is a random number generator that has specific properties. It is a cryptographically secure random number generator, or CSRNG. What is the difference between a cryptographically secure random number generator and one you made based on introduction to Python articles you read in a book?
That I did not generate.
That one works. The one you tried to hack together is why you got your money stolen. Random number generators are very difficult to do right. Don't try this at home. This is not DIY stuff. Actually figuring out how to create a random number generator that evenly distributes output across the entire possible space of numbers it's supposed to generate is a hard problem. Really, really smart mathematicians do this work, and they often do it wrong. All right, so I don't build random number generators, and I've been in cryptography for almost 20 years. Instead, I rely on industry-established, properly peer-reviewed, cryptographically secure random number generators. So the first lesson in this is do not try to do this yourself. Find a proper cryptographically secure random number generator. Most operating systems have either a source of entropy or a library with cryptographic secure random number generators, or both. For example, in Java, secure random. In Python, the random library, etc., etc. These are properly approved cryptographically secure random number generators. The next important step is seeding that. A seed is the initialization of a cryptographically secure random number generator. That is a starting point of randomness. And then you create further randomness by putting it through this. That is usually sourced from the operating system. Operating systems have ways of producing randomness through user activity. Wiggle with your mouse, type some keys, listen to the sound that's coming in from the microphone, and such a gain that it's picking up cosmic radiation pops. You can do all kinds of things like that. At Stanford, they have a long-running project that uses a webcam pointed at a lava lamp and looking at the little colorful bubbles. And that is a really good random source. True randomness is impossible to prove, and a topic of really difficult study. There's actually an XKCD comic, if you read those, where they're taking, or maybe it was Dilbert, I'm not sure, I think it might be Dilbert, where they're taking them on a tour, they say, this is our random number generation department. And there's a guy and he goes, 6, 6, 6, 6, 6. And they walk away, and then Dilbert, I think, observes, well, given just a sample of 6 numbers, that may in fact have been part of a larger random sequence. And that is scientifically correct. And that's why you never know if a random number generator is actually random. All right, so get one from the operating system, feed it into a cryptographically secure random number generator, produce a random number. That random number will have an amount of entropy in it. In cryptography, entropy is measured in bits. That means how many bits of randomness exist, or how big a bit sample can we pull from this that is still random. And if you try to pull more, then it's no longer random, right? So you need to find a source that will give you at least 256 bits of randomness. Preferably more. Start with a larger source of randomness. Maybe pull a couple of kilobytes of randomness. Here's the next trick. One of the most convenient ways to convert that into a very simple 256-bit number, evenly distributed across the entire search space, is to feed that random number generator into SHA-256. SHA-256 is a secure hashing algorithm. It will take a random data stream and it will convert it into a fingerprint, which happens to conveniently be 256 bits. So if you take randomness, shove it through a message digest or hash, and come out with 256 bits, what you have is 256 bits of randomness, perfectly packaged, ready to turn into a key. The output of this is your private key. Down. That's good. If you start with a low-res picture and try to compress it up, not good, right? What you create is artifacts. This is no longer 256 bits of entropy.
Right. But if you're feeding into SHA-256 and it's scrambling it, it's going to be still going to be pretty hard for someone to figure out where the limits of your randomness are.
Pretty hard. Impossible.
Okay.
We're going for impossible. Private keys, putting money on them. You're absolutely right. It's good in a pinch, but that's not the right way to do it. This process is the correct process for generating private keys. So, depends on the operating system. On Linux, for example, if you're pulling from devu random, what you're pulling is actually one of these in a box. So, a properly implemented operating system, if you can rely on it, a specific source of cryptographically secure randomness, not dev random, devu random, which is entropy controlled. It will not give you more bits than it actually has in entropy, is this. Now, if you pass it through this twice, it's a bit of extra work, but just to make sure, do it this way. All right, so now we've got a 256-bit number. Yes?
Is it the full space that qualifies as private keys? I thought some part of it.
It's not exactly the full space because this is done over a prime field. Elliptic curves are done over prime fields of order p equals 2 to the 256 minus 2 to the 32 minus 2 to the 9 minus 2 to the 8 minus 2 to the 6 minus 2 to the 4 minus 1. Something like that. That's the prime number used to initialize the elliptic curve. That is the upper limit of the elliptic curve. So it's actually this much less than 2 to the 56. The chance of you actually randomly falling into this relatively tiny space is low, but yes, you're right. So the constraints are. Now, the nice thing is that you'll know, because what happens is in the very next step, when you try to validate this by producing the equivalent public key, it will fail because it's outside the field of the elliptic curve. Yes?
Real quickly, the seed is your microphone, noise input, or your random mouse.
Yes. It's just an initialization factor to ensure that you're not always starting from the same random number sequence. Yeah. All right, any other questions? All right, moving on. So now we take this private key and we could represent it in a number of different formats. When you look at a private key, you may see it looking different ways. And that is confusing at first, but it's all the same thing. It's all the same number. It can be represented in a number of different formats. If I take this number and I show it to you in binary, hex, or octal, it's still the same number, right? If I put a checksum on the end and a version byte at the beginning, so that it's difficult to accidentally mistype it, it's still the same number, but it appears different in every one of these formats. The three formats we're going to look at very quickly are hex, base 58 check, also known as WIF in this case, and base 58 check compressed, or rather WIF compressed. Let me write this down again. WIF, which is a base 58 check, and WIF compressed. Which is also a base 58 check with one slight difference. All right, so hexadecimal. Hexadecimal 256-bit keys will give you a 64-digit. Each hexadecimal digit is 4 bits, 64-digit hex number. So, 0F, A, B, 1, 1, 2, 2, 1, 1, 1F, whatever. Okay? And it will look like that. That's the pure hexadecimal representation of this full 256-bit key. Now, normally we don't use it that way. If you've seen a private key in Bitcoin, what does it look like? Anybody? Yes? What does the private?
It always starts with 5.
It always starts with 5, yes. Indeed, it always starts with 5. Why does it start with 5? Because it's using a format called base 58 check. Base 58 check is the same format that makes every Bitcoin address start with a 1, that makes every Litecoin address start with an L, that makes every testnet address start with an M, and most importantly, that makes every Dogecoin address start with a D. All right? Same thing. What you're seeing in all of these addresses is the version number. And the version number is different for each of these encodings. So, in a WIF, the version is decimal 128, or hexadecimal 80, right? Yes?
Does the 5 correspond to essentially like you pump that through an algorithm and you should get 5? Or?
Yes.
Okay, right.
The 5 corresponds to this.
Okay.
So, decimal 128, 80. Right? Okay. So what this does now is you append this, or rather you prepend this, to the beginning of the key. So you take the hex, you add to the beginning of it the version number. All right, that's in hex again, right? And then you add to the end 32 bits, which is a 32-bit checksum. This is produced by double hashing this part You take this part, version plus hex, you pass it through double hash SHA 2 times, and then you take the last 8 hexadecimal digits and you append them. And that's a checksum. That makes sure that you can't mistype this address by accident, right? Just a standard checksum. Right? Base 58 is implemented in every Bitcoin library. Base 58 check, which is base 58 with a checksum, is also implemented in every Bitcoin library. You can write it in Python in 3 or 4 lines, pretty easy to implement, right? So if you want to go out and look at your favorite programming language, go to GitHub, find one of the projects that implements Bitcoin tools in that language. In C, it's PicoCoin, or in Java, it's Bitcoin J, and Python, PyBitcoin tools or PyCoin. Use one of these languages. Go and check and find in the source code base 58 check, and see how it's implemented. You'll understand it. It's pretty simple. What this does, when you take this hex address, wrap it by prefixing it, and then putting a checksum at the end, and then you take all of this, and you convert it into a base 58 alphabet. Who's familiar with a base 58 alphabet? Everybody? Okay, who's not familiar with a base 58? Okay, so a base 58 alphabet is taking all lowercase letters, 26, plus all capital letters, 26. That's 52.
0 through 9.
Plus 0 through 9, which is 10, gives us 62. And then you take out 6 letters. And the 6 letters you take out are 0, or 6 letters and digits. 0, O, lowercase o, LL1. No, LL. Right? So you take out letters that are confusing. L's look like 1s, O's look like 0s. So you take out the O's, you take out the 0s, you take out the L's. And what you're left with is 58 remaining characters. And then you just use those as an encoding scheme. It's like base 64, only it's missing some things that can be confusing. Make sense? Base 58. It's really simple. Again, if you're implementing this in code, you write all of the characters in an array, and then you index that array by the value you're trying to calculate, right? And you just use the subscript to index that array and find the correct character.
This was because Satoshi didn't like the O's and the zeros and the ones and the L's.
Sorry?
Satoshi didn't like the ones and the zeros and the L's.
Easy to confuse.
Well, the problem is when you're reading it off paper, and if you try to type it in, it's something that people often confuse in passwords. It's the same reason why you don't have them in license plates in cars, right? There are no Q's and O's and numbers like that. Yes?
I have a question. Why do you do the double hash in your chess?
Pretty much all of the places in Bitcoin where you see this, we do a double hash. It's just harder than doing a single hash, and it provides an extra layer of randomness. What that means, by the way, is that the reason we use a double hash for the checksum is because we already have the double hash function written in the library because we use it elsewhere. But double hash is also used in generating public addresses, which we'll see in a bit. And that's so that they are not reversible. If you have a Bitcoin address, you cannot even tell the public key, let alone the private key. So we'll talk about that in a second. All right, so we take the key, that's just this hex number. We stick a prefix, we stick a checksum, we convert it through we stick a checksum based on double hashing. We convert it through base 58, and what comes out?
Long string of stuff.
A long string that starts with 5xxxxx, blah, 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 blah. And that's a private key encoded as a base 58 check encoded, right? Yes, everybody get this? So, 2 types of private keys. One of them just has an extra 0, 1 on the end and a different prefix, K or L. That means a compressed private key. Otherwise, normal private keys start with a 5. Unless they're just in hex notation, in which case they are a hex notation of 64 digits in hex that starts with whatever it starts with, because it's a random number. Yep? So far, so good? Does everybody understand why we use base 58 check? You cannot mistype one of these without noticing. It provides error detection and correction within the algorithm. This is very important if you encode this in a QR code. The software can detect if there's been a misscan. The software can detect if there's been a mistype, because it will be an invalid address. It's exactly the same reason why the last 2 digits of your credit card number are actually a checksum based on the previous digits, so that a credit card number can be identified as incorrect without even having to look up anything in the database. Yep? All right. And since a private key is just a random number, there's no other way to tell if it's wrong, especially if it's just hex. So you need a checksum. All right, so we've got private keys. Moving on. Now we're going to take the private key and we're going to convert it into a public key through a process of multiplication. Now this is some weird-ass multiplication, because we're going to do it in an elliptic curve on a prime field. And that's a lot of fancy math for jumping around from dot to dot on a very big piece of paper. You start off with an elliptic curve. The elliptic curve we use is something like this, and it's y squared equals, y cubed equals x squared plus 7, or whatever. It's the sec P256 K1 Koblitz curve. It's a standard curve used in elliptic cryptography inside Bitcoin, but basically it looks like this. The process of adding 2 numbers on an elliptic curve can be geometrically represented by drawing a line from one point through the curve until it intersects, creating another point in the curve. So P, Q, Q prime. And the points are reflected across the curve, and multiplication is equivalent to drawing a line, or rather addition is equivalent to drawing a line. Multiplication by a number means addition many times. So it's drawing a line that bounces back and forth across the curve in different places each time. I like to create an analogy for you, which is like this. You got a billiard table, right? I put down the white ball, and then I hit it. If I hit it exactly the same way, it's going to bounce perhaps 1,000 times, and it's going to end up in exactly the same position. After it's bounced 1,000 times and landed in a position, you have no way of figuring out how it bounced and at what angle I hit it. But I can redo that every single time. So I can hit the ball and it will land in the exact same spot, but you cannot figure out the path just by looking at where it landed. Make sense? That's an irreversible, mathematically irreversible function. That's what we're doing in elliptic curve. Another example in real life. If I take the color yellow and the color blue and I mix them together, I create a shade of green. I can create the same shade of green by those 2 colors every single time. There is no way you can reverse engineer from the shade of green which precise yellow and blue I used. Right? That's a one-way function. Mixing colors, easy. Unmixing colors, impossible. Right? In mathematics, that's the process of factorization, a discrete logarithm. Right? Exponent and discrete logarithm. Raising something to a power mod p versus trying the discrete logarithm mod p in reverse, the basis of public key cryptography. The elliptic curve doesn't actually look like this because it's on a field of primes. And what that means is that what the elliptic curve looks like is a series of dots, specifically about 10 to the 70 dots. 256 bits, 2 to the 256-bit dots. Half of that above the axis, reflected half of that below the axis. The process of doing multiplication on this field is like doing this. Right? Only you're doing it with a number that's 256 bits long, so you make 256 bits worth of these little jumps. And you land somewhere. And where you land is your public key. And there's no way to work that out backwards. That's what it looks like. But there's an easier way of writing it. The way to write it is this. So that's private key times a constant. This is called the generator point. It's a fixed point within the Bitcoin ecosystem. G is always the same for everybody. You just multiply this by the number K, which is your private key, which you got here, and that produces your public key. This is a point on the curve. This is a point on the curve. This is simply a multiplier. This is not a point on the curve. Okay? Even simpler way to write this is what you're doing is you're taking the general point and you're adding it to itself k times, where k is your private key. And that causes it to bounce all around the elliptic curve until it lands on that point, which is your public key. Okay? Now, in programming, what you're going to do is you're going to have a library that's called something like EC multiply. And you're going to have a point that's called G, and you're literally going to write EC multiply K, comma, G. And the result you're going to get is going to be your public key. So you don't need to worry exactly about how this works. So it is a multiplication over a group field defined on an elliptic curve mod a prime number, a very large prime number. Yes?
Is the runtime of the multiplication linear with the size of the key?
Excellent question. Really good question. The multiplication is actually a very low cost operation. Elliptic curves, which is the one used here, have some efficiencies built in. You can do about 70,000 multiplications. Not the individual steps, the full multiplication. You can generate 70,000 keys, public keys, per second on your average laptop. Right? To break one would take you 70,000 trillion years. But you can generate 70,000 of them a second. Okay? So this is a very, very inexpensive operation. So you do this, and you get a public key. Now, a public key is a point.
Question.
Yes?
Is it required to use G, or can you use any?
No, it is required to use G. That is the definition of how you do private keys for elliptic curve digital signature algorithm according to the National Institute of Standards Security Group, SecP, that define the SecP 256K1 curve. So this is based on an international standard.
But the G of the Bitcoin network that is the same across the network.
The G of the Bitcoin network is actually the G of this curve in the NIST documents.
Right.
So it's even broader than just the Bitcoin network.
Okay.
Yes.
And the choice of G is also quite well thought out, I guess.
The choice of G is a very large prime as well.
Yeah, and I thought about which prime, I guess.
It just had to be a large one.
Just any point.
It really doesn't matter. There are a few points that create weird effects, but other than that, most other points are fine.
Just to be
As
clear.
far as I understand, I mean, my knowledge of elliptic curve has almost been exhausted. We're probably 2 questions away from exhausting.
So just to be clear, if you use a different G in your algorithm, it's not going to work.
It's not going to work because nobody else will be able to recreate that. And they won't be able to validate signatures that you create based on that. All right? It is going to work in terms of you're going to produce a point.
Yeah.
It just won't be a point that anybody will be able to use. All right, so now you've got a public key, and that's defined as 2 coordinates, x and y, in the elliptic curve field, right? For simplicity's sake, think of these coordinates as just 2 big numbers, right? And what we do now is take these 2 big numbers and write them down in hex as follows. So the hex representation of a public key is 04 x, y. This is 32 bytes, and this is 32 bytes. Which produces a 130 character long, 128 plus 2, 130 character long hexadecimal number that starts with 04. By the way, you can try all of this out. One of the easiest places to do this is to go to bit address, right? Go to the last tab of bit address that says wallet details. Paste the private key in there, and you're going to see the private key as hex, as base 64, as a base 58 check encoded as a base 58 check encoded compressed key. Then you're going to see the corresponding public key as hex, starting with 04, as a base 58 check encoded public key address, starting with 1, etc., right? And a compressed point.
Is it called bit address?
Bitaddress.org. It's probably one of the most useful bits of software. You can do paper wallets and all kinds of other things. And it does everything in JavaScript in your browser, so the keys never leave your browser. All right, any questions so far? All right, so if you take this and then you create a base 58 check encoding, well, actually no. Sorry, this is the public key. Now from this we create an address. And an address is created through an irreversible process of hashing with 2 different hashing algorithms. The first one is RIPE MD160, and the second one is SHA-256. Yeah? One, 2. We get another piece of hex. Yes? So far so good? We take that piece of hex here and we put a prefix of 00 and a checksum. And we produce a base 58 check encoding of this. That is 1. And that's your Bitcoin address.
I think you have to flip the SHA-256 and write MD.
Is it the other way around?
Yeah.
The magic of whiteboards, those are inverse. So first you SHA, then you write MD. Thank you.
Just write this.
He's the one who's going to be answering questions after I leave.
Write
Yes.
MD generates a shorter hash, so
Right.
you start with the bigger one and then the shorter one.
That makes a lot of sense. Right? So what you're left with is a 34 character plus prefix. Then you base 58 check encode that. Okay? Let me delete some of this. You got this. All right.
So technically the address is not all the public key. Well, that's
The address is not the public key. In fact, if you have an address, you cannot figure out what the public key is. There's no way you can go this way. However, you can find a signature on the blockchain made for this public address, then it reveals the public key. So when you ask software to give you the public address that corresponds to a Bitcoin address, what it does is it goes on the blockchain and tries to find a signature that matches this, and from that signature find the public key. So it's only if you've made a signature that you've revealed your public key. Until that moment, all you've given out is an address, which is irreversible. Yes?
Why don't we use the public key as an address? What's the purpose of that extra step? Because
Obfuscation.
And shorter, I guess.
And it's much shorter. And I don't know, there might be other very good reasons. Various types of cryptographic attacks, lengthening attacks. Who knows?
Hypothetically, there was some way to derive the private key from the public key with enough computational power to be harder to do it. And
Also,
yeah, but if you
job
have 40,
security
50, 6 layers.
for Bitcoin developers. Because this shit is so complicated that it takes seminars like this to explain it. So that way people are employed.
So after this, the public key doesn't reappear, it's thrown away.
No, this the public key, well, okay. So the public key, as I mentioned before, can be easily generated from a private key.
Yeah.
Right? So you don't actually need to keep it around. You can generate it on demand. You don't need to keep anything around other than the private key. Everything else can be derived. And it will be derived in a deterministic manner. A private key, let me make this clear, a private key generates the same public key, which generates the same Bitcoin address every single time, right? So if you just store the private key, you can regenerate everything. If you have the public key, you can generate the address, but you cannot generate the private key. And if you have the address, you can't generate anything. All right, so far so good? Now, I mentioned before that this is stored as 04xy. If you see a hex representation of a public key, it will look like that, 04, and then 128 hexadecimal digits, which represent the x and y points. Elliptic curves, if you remember, are symmetric across the x-axis, which means that the y is either a positive or a negative point. Yeah? But it's always the same one. So you drop the y. If you know the x, you can find which part of the curve it's on. So all you need to know is it above or below the axis. You know where it's going to be. Let me draw this out for you again. This is the elliptic curve. If I know x, I know that my y is either going to be here or it's going to be here. So all I need to know is it a plus y or is it a minus y? And therefore, I don't need to store the y. And the y is 32 bytes. So I can save a lot of space by simply removing the y. So far, so good?
But storing the sign.
Huh?
But storing the sign.
You just store the sign. So then you store this as either 02x or 03x. And I can't remember which one's positive and which one's negative, but one of these prefixes means that the y is on the below the x-axis, and the other one, I think this one means it's above. I could be wrong, right? One or the other. But basically, if you see a public key that starts with 04, that means it's uncompressed, and it has 130 characters. If it starts with 02 or 03, it is a compressed public key. And in one case, it's a compressed public key with a positive y, the other one is a compressed public key with a negative y. You can easily recreate the y by redrawing the point on the curve. There are libraries to do that. And you've saved 32 bytes. So this will be 98 hexadecimal characters instead of 130. Something like that. Yes?
And when you're saving characters like that, are you optimizing for reducing the size of data that you're transferring across the network? Or what are the benefits to keeping this so short?
Keeps the wallet size smaller.
Okay.
So if you think about it, you've cut all of the public keys in half for the wallet size. Also, yes, public keys are introduced in the encumbrances on an output. So I think it also saves data on the network. Yeah. Okay? Yes?
The network stores the public key, or I'm not too sure I understood that. Because I thought that the address was what was stored. Right?
That's a good point. No, only the address is stored. Not sure.
Creates jobs.
Sorry?
It creates jobs.
It creates jobs. No, it's more than just the wallet. I think it does affect the network storage. Perhaps in the digital signature you could use. Because I think in the digital signature you provide the public key plus the signature.
The script, right? The
Script
script from the script from the previous transaction
Yeah.
contains the public key.
It contains the public key itself in full. So
Yeah, I'm just
there
not
you're
sure.
saving 32 bytes
Compressed or not.
if you're compressed. So you would say network traffic. You would also say blockchain traffic because that gets listed as a transaction. Every transaction has at least one public key signature. So if you save 32 bytes for every transaction, that's a pretty big deal. All right. So if you take these and then you produce through this process a base 58 check address, the version 00, which corresponds to Bitcoin, the currency, main blockchain network, not testnet, that's what 00 means, will always start with a 1. So you cannot tell from the prefix of the address if it is compressed or not. Yeah? If you unbase 58 check, they're actually slightly different length. When you unbase 58 check it, you can see that the hex in here is 32 bytes shorter, right? So far, so good?
Why shorter?
Oh, it's not, because it came out of the SHA-256.
Yes.
So it won't be shorter, you're right. Sorry. See, that's an example of the things that I say that are wrong.
But the address can be generated from any form of public key.
Yes.
Right, uncompressed doesn't matter.
So you wouldn't know which it is.
Okay.
Yeah. So what happens is you end up with addresses that look different, but are based on the same public key. Different representations of the same public key, but they're also based on the same private key. Right? This can get confusing.
Well, only 3 addresses.
No, only two addresses.
Oh, sorry, yeah.
It's either going to be one of these,
Yes,
or it's
yeah,
going to be
right.
one of the 2 of these. So it's either this or this. If you go to bitaddress.org and you put in a private key and you generate, it's going to generate both the compressed and the uncompressed Bitcoin address, both of which start with a 1, but look different, right? So that means 2 addresses can correspond to the same public key. That's something to remember. Yes.
Can I actually use both of those addresses to then receive money into the same
Yes,
place?
because what the address does is it provides an encumbrance that can only be resolved through a signature by the private key. How many private keys are there? 1. So 2 addresses that put an encumbrance that can both be solved by the same private key signature means that the money is owned by 1 private key.
It's messy.
It's messy, and it may look like different addresses if you don't account for it properly. Yes?
Sorry, could you explain the use of the word encumbrance a bit more? I'm not
Okay.
sure how to visualize where that's.
Right. When I send Bitcoin to you, what I'm doing is I'm creating a transaction whose outputs have your address listed as a padlock that only you can unlock. There are 2 different types of padlocks, but they both open with the same key, the private key you have. So I can put a silver padlock on it or a gold padlock, but they both open with the same key that you have.
And when you use the term encumbrance, what part of that process is it referring to?
So an encumbrance is what it means to take a transaction output
Yeah.
and encumber it, meaning burden it
Got it.
with the requirement that someone presents a key. So sometimes you're encumbering an output by saying this is encumbered by a public key, which means that someone needs to sign something. Other times you're encumbering it with a script address if you're doing a pay-to-script hash, in which case someone needs to present a script and the necessary signatures to satisfy that script in order to resolve that encumbrance. Other encumbrances might involve contracts in the future, right? In general, it's not just a payment to an address. It's a payment that basically requires someone to present cryptographic proof of something. The most common something is a digital signature with a private key that proves that they own the public address that they used to receive the money and thereby resolve the encumbrance placed by the sender. If that made any sense.
Yeah.
You want to try that again?
Just
Yes.
Let's do questions.
Just to extend what he was asking. So for the so in order to test it, that this is really your, you don't want to present your private key to network, right?
In order to test the validity of your money, you sign and you present a public key and a signature that can be verified against that public key as having been created by its private key equivalent.
Yeah.
And someone with the public key and the signature can verify it without knowing the private key.
Okay.
And that proves your ownership of that public key. And since that public key can be resolved to the address on which the encumbrance was placed, that proves your ownership of these funds.
Right.
So you sign and present a public key. The recipient or the person verifying this transaction says, I see a public key. Does this signature correspond to this public key? Yes, it does. Does this public key, if I turn it into address, correspond to the address that placed the encumbrance on these outputs? Yes. That means this person owns these outputs, and therefore they can spend them, and therefore this transaction that is using those outputs is properly signed and valid. Yes?
So you get a wallet, and with that wallet you get typically, I believe, 20 addresses. Does that mean there are 10 private keys for the wallet?
No. There are probably 20 private keys for the wallet. It doesn't generate both compressed and uncompressed. Most wallets nowadays do compress public keys. Yeah, some wallets use compressed, some wallets use uncompressed. Most of them are not compatible with each other, which leads to all kinds of confusion when you're trying to import wallets from one format to the other. Yes, but they're easily converted, right? They all correspond back to, fundamentally, a number, a 256-bit private key number that is the same, and from which you can generate all of these other representations. Yes?
So in theory, we have two types of addresses, but you could create your own generate a public address from your private key.
But no one would be able to validate that, because everybody else needs to validate it when they see the signature.
But if they don't know the type of, if they don't know whether it's compressed or not, how do they?
They do know whether it's compressed or not, because in the signature you
Oh,
present
right,
the
the signature
full public key.
okay.
And that's how people can find out the public keys behind addresses, because they just look and see if you've signed before. Right? Okay. Thank you for that. I think public keys. Let's move on. So we've now done ECC generating formats in an hour. This was overly optimistic. So we're going to do the rest in 10 minutes. Actually, it's going to be fairly easy. So what I've described is type 1 non-deterministic keys. And the reason they're called non-deterministic is because they're randomly generated through the process we saw with a cryptographically secure random number generator. Or rather, every single one of them is randomly generated. So for example, you have a Bitcoin D wallet. It has 20 keys in them. How was these 20 keys picked? Like this. Random number, K. Random number, K. Random number, K. Random number, K.
These K are not different. Right?
These are all different. From those public keys, from those addresses, right? So you generate from a random number, a private key, a public key, and address. Then you throw the dice again. Random number, private key, public key, address. All right. Now, what does that mean? Bitcoin D also generates change addresses for pulling back change when you do a transaction. Also, one of the best practices you can do is to use a different address for every transaction. How many keys do you need to back up based on this scheme? All of them. And every time you generate a transaction which has change, therefore creating a new address, therefore creating a new key, or is not reusing but is generating a completely new address just for that transaction, you will need to make another backup of your wallet. Okay? That is the disadvantage of type 1 non-deterministic keys. You need very, very large backups. Okay? And you need to take backups all the time, every time you do a transaction. Yes?
So you can pre-generate the keys, right? Isn't that what Bitcoin D does?
Bitcoin D pre-generates keys in a pool.
Right,
And so it doesn't need to back them up every time, but still, every time it generates new ones, it still has to keep the backup of every single key. Yes?
Why would I want to generate an address every time? For every transaction?
Privacy.
Right, so nobody can track.
So nobody can track the links between addresses. That's the best practice in Bitcoin. Yes?
Why would you hold on to your old private keys if you don't expect to use the addresses?
Because some idiot might send you money to an address that you've long stopped using, but they happen to find this in an old email, and then they sent you money, and that's why I never delete private keys. Because you can always delete a private key. You can never undelete it. So never delete it. And that's exactly why the wallets end up being huge. Right? All right. So it also exposes you to risk because you've got a big file with a lot of keys flying around in there. And managing all these keys gets very complicated. So, two solutions. Type 2 deterministic wallets based on chains. Type 2 deterministic wallets based on trees. Type 2 deterministic wallets based on chains were first introduced in Electrum.
Type 2 based on chains were introduced in?
Electrum. Electrum is a wallet, and it uses type 2 deterministic keys. These are also now used in Armory, as well as the bits of proof enterprise class server, and they're implemented in a number of other systems. SX tools, if you haven't looked at that, that's one of the things we introduced in one of the hackathons. It's the libbitcoin command line tools. They also handle type 2 deterministic chains that are Electrum compatible. So far, so good. The simple idea is, from the random number you generate a hexadecimal seed. This seed is the generator for all future addresses. From that, you then use a mathematical function to generate keys in such a way that you cannot predict these keys without having the seed. So if you have K1, you can't figure out K2. If you have K2, you can't figure out K1. Right?
So even if your private keys are compromised, as long as the seed is not compromised, you're still fine.
You can regenerate everything from the seed, all of your private keys, all of your public keys, and this can keep going forever. There is normally a gap, which is that instead of generating every single, you generate K1, K6, K11 every 5, right? That's called a gap of 5. So the keys that you're generating are spaced apart.
Is that number arbitrary?
You can pick an arbitrary number. If you do, then it will generate different keys if you change that gap based on that same seed, which is why they tell you to remember both your seed and your gap when you do this. This provides a bit more variation in the keys. Yes?
If someone has access to my hard drive, can
Yes.
they copy it to the keys to their hard drive?
If someone has access, they can copy all of this. Yeah. Or they can steal the seed. So these things are usually stored encrypted. Both when they're type 1 non-deterministic keys, where they're just random number key, random number key, random number key, random number key. You have to keep those things encrypted. So on Bitcoin D, that's done with the wallet passphrase command and the encrypt wallet command. In Electrum, it's encrypted using a different system, et cetera, et cetera. Usually when you type your password in order to open your wallet, what you're doing is you're decrypting your wallet from the hard drive. Yes?
So if someone did have access and I had kept a backup with me on the seed for my precaution, and they had stolen my keys and using my keys on network for whatever purposes, and I realized that it has been stolen, so for my seed I tried to regenerate. Will there be a kind of a conflict network? Will the network see that there's two people with the same keys which are...
The network doesn't look at keys. You would have to generate transactions to empty any encumbrances that were against those keys. You'd have to go out on the network and create transactions that claim funds locked onto those keys before somebody else claims them. Yep.
Was your description of the seed and your G a KDF? Are we going to talk about key derivative functions?
We're not going to talk about a KDF because it's a bit complex. How this is generated involves a KDF, right? Key derivative functions and key stretching algorithms are used for a number of different reasons. One is to generate sequential keys that are not relatable, right? Normally this is done with a one-way hash function. But they're also used to stretch the computation required to generate multiple seeds to try to brute force a system. So for example, you do 20,000 repetitions of script, which is the proof of work algorithm and password stretching algorithm used, or PBK, DF2, or whatever it is. What this does is it makes it much harder to do a brute force attack because it increases the computational requirement for every single attempt. On your browser, it will take 3/4 of a second. But you try to do that with 1 trillion keys, that's 3/4 of a trillion seconds.
Real quickly, if you, let's just say that somebody becomes aware of K1, K2, K through 1000, does it have the possibility to leak your seed or some
No.
way? Okay.
So these are one-way functions, and these are one-way
These are
functions.
okay.
On purpose. So if you have K1 or K1 through K infinity, you cannot derive the seed. If you have a subset of Kn through m, you cannot derive Ks that are not in that subset. Yes? But if you have the seed, you can derive everything, which gives you a perfect backup.
So go back at the seed, and then I import in a different wallet.
Yes. It
How
will
the
generate.
wallet will know how far to go to access all my funds?
Great question. How does any wallet know how far to go? Very simply. What it does is it starts and it takes K1 and generates the address. And then it goes on the network and says, any transactions for K1 address? Yes. K2, K3, K4. And it goes until it finds no more transactions under those addresses. And then it says, well, you probably got this far. So it will start trawling the entire sequence or chain, looking for all transactions until it finds a gap. Usually what it does is looking for 100 consecutive addresses after the last one it found a transaction for which there are no transactions before it decides, I've now found all of the keys that were used. Yes?
Now, does that have to tax the network, or can you just locally search the blockchain?
Yeah, you just search the blockchain.
Okay.
Yeah, when I say the network, I mean, yeah. That's, you can't actually search the network.
Yeah.
You have to have a blockchain copy. You can use blockchain info API.
And this works because wallet uses those keys like from beginning
Yes.
every time, not like, oh, I will skip 1,000 keys and start with
No, the wallet uses a specific pattern of key
Every
generation for change, and each time you use an address, it moves to the next one.
Next one.
So you will see transactions for every one of the addresses. Sometimes there's little gaps,
Right.
but they won't be very big. So if you say, let's look for 100 keys after we run out of gaps, then you're like, okay, this is definitely the final gap. This is how far we got. Yes?
You say the transactions saved in the blockchain.
Yes.
Where's the blockchain in your hard drive?
Well, the blockchain is everywhere. It's on everybody's hard drive. So everybody has a copy of the blockchain, or what they think is a copy of the blockchain with the longest difficulty chain of transactions in it.
So how big is the size?
26 gigabytes in last check. Yeah. It has every single transaction since November 3rd, 2009, which was the Genesis block.
And it's in
November 13th. Sorry.
in everybody's hard drive.
Everybody's hard drive. Right. If you have a full node client. You can also have a lightweight client, and that just asks another server that has the full blockchain. All right. So far, so good. Now, this is where it gets really easy because I can check off this one very quickly. BIP 39 is a new standard that's coming out now. It's based on the Electrum model. What it does is it allows you to take a hexadecimal number, which is a seed, and produce 12 words. Coffee chair, asparagus, pawn, tea kettle, orange, you know, whatever. 12 words. These words are deterministically derived. You can convert those 12 words back to the seed. So if you are asking your girlfriend, wife, husband, brother, sister to help you restore your Electrum wallet because you lost it while you're on a trip in Thailand, and they're trying to read the seed over the phone, instead of reading 125F0H whatever, instead they're reading orange, coffee, kettle, barbecue, right? And so those 12 words will reconstruct that same seed. Yes.
Is it restricted to English in any way?
Sorry?
Is it restricted to English in any way?
It is restricted to English entirely.
Is it?
Yes.
Okay.
It is actually restricted to a specific dictionary. And the reason for that is because based on this specification, every single wallet in the world can take 12 words and deterministically recreate the same seed from which it can then recreate the same keys.
And any randomly generated set of 12 words can be turned into a seed, or is that, well, that's
There's a
seed
checksum built in. So one of the words is a checksum for the other words, so that no, it will say those are not correct.
How big is C?
How big is what?
C, that's C, in bits.
The seed is usually 32 bytes.
So I don't need to back up my wallet anywhere, as long as I remember those 12 words.
Correct.
And
And that is something you can do with Armory, and that is something you can do with Electrum. That is something that you will be able to see in more and more wallets. Now that this has been standardized and a cross-industry standard, this was recently published, and it's going to make backing up and restoring wallets a lot easier. It's also going to make it easier to transfer type 2 deterministic wallets from computer to computer, from different wallet to different wallet, simply by transmitting 12 words. Yes?
Why has the QT client implemented? I mean, is it just a wait and see approach, or?
Because the QT client is more focused on implementing the stability of the core Bitcoin protocol than implementing user-based pretty wallet features that are actually already broken, have an absolutely horrible graphical user interface, and as of recently were removed from the Bitcoin.org site as the recommended wallet for new users because it absolutely sucks as a user interface. So I'm glad. They're not going to, I don't think you're going to see much development of the reference client as a wallet. In fact, the current discussion among developers is to strip all of the wallet functionality out, do it over RPC, separate the wallet file from the main routing node and blockchain database, and then that will enable other wallets to be built on top, which are not going to be implemented in QT.
But
Yes.
why RPC?
Does the order of the 12 words matter?
Sorry?
Does the order matter?
The order of the 12 words matters, yes. And if you put it wrong, it will check the checksum and find you're wrong.
Why RPC?
RPC is just easy, that's why. It's because RPC and inter-process communication on the same machine are almost as fast, and it's very easy to do separation of security controls that way and to isolate components. It provides a clean API layer between the two. And it's very common in any language to implement just basic JSON RPC.
Is there any functionality in BIP that allows someone to send coins to an address that then somehow get sent to another address? It's
A cascade address system.
yeah.
No.
No. Okay.
But you can do a multi-sig pay-to-script hash, which we talked about at another seminar, and we're going to revisit again in more detail. All right, so BIP. It stands for Bitcoin Improvement Proposal. It's a series of, it's like the RFC process on the internet, and you can find these bits on the GitHub under the Bitcoin organization. Each one is basically a text document that says how this will work and how to implement it correctly, and then people can implement it. 39 is the mnemonic code. This is called the mnemonic. From the Greek word mnemi, which means memory. This is a memory trick. Yep, mnemonic. All right, so that's BIP 39. I'm going to do BIP 32 and BIP 38 very quickly.
You've mixed your indexing.
Huh?
0.
It happens.
No, I haven't.
You started with 1 in the second sequence.
Oh, yeah. Yeah.
That's alright.
Okay.
0.
Alright. But it's decimal, not binary. Alright, so BIP32 is called the Hierarchical Deterministic Wallet. Hierarchical because it forms a hierarchy in the form of a tree. It's an n-ary tree, or one that has n branches. And this is actually a 32-bit n-ary tree. That means there are 4 billion branches per branch. Yeah? You can get seriously lost in this key space. What this is basically the same concept as before. A random number generates a master key from which you generate a series of private keys, which can then have subkeys, which can then have subkeys, which can then have subkeys to infinity. Right? And each of the subkeys can have 4 billion subkeys below it, each of which can have 4 billion subkeys below that, each of which can have 4 billion subkeys below that. 3 levels deep in the tree, and you're in more than cosmological numbers. Yeah? There's another little trick to this, which is that you can simultaneously deliver the private and the public key and derive them separately. Probably easier if I use 2 colors for this one. All right. So red are public, black are private. Here's where it gets interesting. You can derive sub-public keys from public keys. And you can derive sub-private keys from private keys. Now, of course, you can also derive like that, right? So if you've generated the private key, you can generate the corresponding public key. But here's the really magic trick. Through the magic of elliptic curve mathematics, you can have a public master key from which you generate a series of public child keys without knowing the private key. Why is this tremendously useful? Let's say you've got a web server that needs to sell widgets, and you want to generate a unique transaction address for every customer and every widget and track them independently. You can take just this thing and put it on the public web server. The web server has no private keys, but using the master public key, it can generate an infinite sequence almost of sub-public keys, each for a different transaction. It can keep generating public keys. It doesn't know any of the private keys. Back on a separate server, you can now generate transactions that consume any payments to those public keys by knowing this private key, and simply the sequence number for the corresponding public key. Or you can guess them using the same technique that Electrum uses with gaps. You can just keep generating and see if there are any payments against them. You could pre-generate 1,000,000 privates and 1,000,000 publics, and you can use a different one for every transaction. And you can actually generate the spending transactions off the web server, while the web server can generate an near infinite number of keys directly off the public chain without having any of the private information.